Understand what Ka values represent. The acid dissociation constant, Ka, is a thermodynamic equilibrium constant that measures the strength of an acid in solution. A larger Ka indicates a stronger acid that dissociates more completely to release hydrogen ions, H to the power plus, while a smaller Ka indicates a weaker acid that dissociates to a much lesser extent. Compare the given stepwise dissociation reactions. Step 1. H2SiO3 is in equilibrium with HCO3 to the power negative plus H to the power plus quad K. A1 equals 2.1 times 10 to the power minus 3. Step 2. HCO3 to the power negative is in equilibrium with SiO3 to the power 2 plus H to the power plus quad K. A2 equals 5.3 times 10 to the power minus 9. The value of Ka2 is roughly 6 orders of magnitude smaller than Ka1, 5.3 times 10 to the power minus 9, LL 2.1 times 10 to the power minus 3, indicating that removing the second proton is vastly more difficult than removing the first. Analyze the electrostatic charges of the starting reactants. In the first step, the positive proton, H to the power plus, is being removed from a neutral molecule, H2SiO3. In the second step, the positive proton, H to the power plus, is being removed from a negatively charged anion, HCO3 to the power negative. Apply electrostatic principles. Coulomb's law. According to Coulomb's law, there is a strong electrostatic attraction between opposite charges. It requires a certain amount of energy to break a polar covalent O-H bond in a neutral molecule. However, it requires significantly more energy to pull a positively charged proton, H to the power plus, away from a species that already carries a net negative charge, HCO3 to the power negative, because of the strong electrostatic attraction between the +1 proton and the -1 anion. Conclude, because removing the second proton requires a much higher input of energy, the second dissociation step is far less thermodynamically favorable, resulting in a much smaller equilibrium constant, Ka2. This directly identifies option D as the correct explanation. The correct answer is option D. Removing the first H+ from H2SiO3 requires less energy than removing the second H+, because the second H+ is removed from a negatively charged species.